Um, okay, so I'll leave the stage to Livia and Bruce, who will co-chair this last discussion. Please, Livia.
Okay, thank you, Elena. So wherever you are, good morning, good afternoon, good night. Since we are approaching the end of the Budget 2022 conference, Bruce and myself have decided to focus this last discussion sessions on challenges and future perspective for our community, in particular on scenarios and tools, also based on what we have heard during the entire week. So now Bruce will take the chairing of the discussion on scenarios.
Thanks, Livia. Right, so we've heard about scenarios and processes for growth of these inner structures, like when they form or how fast. What remains today, in situ versus ex situ, gaseous or stellar. What maps from high Z to today's structures. So to keep track of all this, Livia and I made this page. Can you see that?
Yes.
Okay, good. So this is kind of the structures we've been talking about. And I've divided them into bulge region and nuclear region. And in the bulge region, we talk about a hot spheroid, which maybe was formerly called a classical bulge. A boxy peanut kind of bar, maybe formerly called a bulge or BP bulge, or maybe a bar. And then we see in other galaxies an exponential shape for that bar. Perhaps they haven't become boxy yet. Maybe it'll just take too long because they're low mass galaxies. We talk about an inner disk, which maybe was called the pseudo bulge, and maybe it was never a bulge because it didn't bulge out. So we're learning it's perhaps an inner disk. The interstellar halo, the inner part of the thick disk. These are the components that we're talking about at this conference. I think it's really useful to bring in some of these new names, which I've heard from you, and not just keep calling things a bulge because they look bulgy, because they now seem quite different. And also in the nuclear region, where we've discussed a little bit, but not so much as the bulge region, including a nuclear disk and of course the molecular zone, perhaps a nuclear bulge, nuclear bar, nuclear cluster, and so on. And what we noticed about these is that they seem quite distinct in phase space, meaning they're either different in position or they're different in velocity dispersion, or even in velocity. So for example, there's a bar, and then the inner disk is inside that. They don't interact too much. The bar would have vertically oscillated the stars in a certain radial range, but the disk is somehow protected from that inner disk. And then there's the hot components, spheroid, halo, thick disk, which because the motions are so fast, they're very hard to perturb. So they're all kind of dynamically distinct, even though they overlap somewhat. Similarly for the components in the nuclear region. So I'm wondering, are they really all distinct in phase space for a reason? That's how they survived this long. And then you have to ask if there are other possibilities. And this is kind of a question for you. If we have some tidally disrupted thing, a globular cluster or a little galaxy or something, could it still be there in a tube-like orbit? Or does everything that comes in have to end up in one of these phase space bins? Because if it came in a little different, it would migrate over to become part of the bar, or move in to become part of the inner disk, and so on. Is this what we have? And so I want to ask both the observers and the dynamicists here to look at the structures in the combination of the morphological aspect and the dynamical aspect as distinct, maybe a basis set for what can there be in the inner part. And if anything that comes in has to end up in one or the other of these for dynamical regions, then that sort of mixes up the chemistry. It mixes up abundances and ages. And we're seeing some of that. There are some correlations between abundances and morphologies, but a little bit of mixture, and that mixture could be even greater in other galaxies, particularly those which may have formed faster. So there's a higher mass component that's alpha rich. So let me stop for a second and give the morphologists and the observers and the dynamicists a chance to comment on this way of segmenting structures in terms of a phase space or kind of a basis set for what can be there. Peter, good, Peter.
Okay, yeah, just a couple of very brief comments on your nomenclature. I would say the inner disk in your upper set and the nuclear disk in your lower set, that's just a single population.
Mm-hmm.
I mean, if you have a bar and if you assume the disk, this nuclear disk is 10% the size of the bar, then when your bar is a kiloparsec, your nuclear disk is 100 parsecs. If it's a 5 kiloparsec bar, your nuclear disk might be 500 parsecs. I don't think there's a distinction there. The other thing is I want to throw in the possibility that nuclear bars, or the inner bars of double-barred galaxies, can have their own boxy peanut bulges, which is something that Jairo noted was, at least in one double-barred galaxy, there is kinematic evidence that the inner bar, the nuclear bar, has its own boxy peanut bulge. And since the orientation of the bars are different, this would be distinct from the boxy peanut bulge of the main outer bar.
Yeah, interesting. Michael. Still can't hear you, Mike.
I had needed to get unmuted. Yes, I think that there are some problems in, everybody can agree that there is a bar peanut or bar that is concentrated in the plane and comprises most of the metal rich population. However, a mystery is that the cylindrical rotation persists even for, down to about the bulk of the population, down to about -1 dex. Below that, maybe not so much, but certainly in Brava, we saw cylindrical rotation as far as the eye could see. And yet there is this component, metal pore abundance distribution, that peaks at about -0.4 dex that we see in BVBS. And it's not clear that that is the spheroid. There might be another spheroid, Andrea Kunder's Haraliri spheroid. So I think that it's also not clear whether within the bar there is some segregation as a function of metallicity that is, and possibly age, that is important. So a great question is whether there are substructures. And then the second thing is, in fact, in some sense, one could divide the population broadly into bar and not the bar, and then say that maybe within those populations, there are some significant substructures. This also gets back to the question of what is the alpha to Fe versus Fe over H measurement, because the K-Rose paper suggests that alpha to Fe can be used as a strong way to segregate populations, and yet optical surveys don't see such a dramatic break. My worry is that there are going to be a lot of spectroscopic surveys that have too low spectroscopic resolution, and further where the abundances are derived by machine learning, and potentially subject to errors in the training set, such that we may miss some of these important distinctions as to what is really going on. Nature does what it will do, and maybe doesn't follow these nice populations that we can identify. certainly it seems like, though, that, a consensus is emerging that the bar peanut is a kind of distinct population, and that you don't see that structure as one moves into the hotter populations below -0.5 dex. But I
Yeah,
just think
so
that's a challenge anyway. That whole issue is a challenge.
you're introducing sort of physical or kinematic substructures, but you talk about chemical components of them. And are they chemically distinct as opposed to physically kinematically? Or are they really different physical kinematic substructures that may have different mixing of chemicals inside them?
Well, what's interesting is back in Johnson et al. 2014, we show a figure of alpha to Fe versus Fe over H from all of the then known surveys that does not show, by the way, a high alpha and low alpha component. And it has always been my impression that one of the biggest surprises about the bulge is the lack of chemical substructure. There seems to be definitely substructure by abundance distribution segregation. So in BDBS, when we go below -500 parsecs or -5 degrees, we see a new shape to the abundance distribution, a new component popping out that is very clear, a metal pore component. But when it comes to composition, where, because of these clumpy galaxies that you first pointed out, at high redshift, where each of the clumps might be expected to have its own enrichment history, you don't see that imprinted into the present day so much. Maybe we just haven't have large enough samples with precise enough measurements to uncover that. But I do worry about, we already have some pretty substantial surveys in terms of numbers. If you add a Gala plus apogee, for example.
Mike, try to get to the point, because there are other people.
Oh, yeah, okay, I'm done.
Let me call
on
Francesca. Thanks so much. That's a good point. And Christina's next. So Francesca.
Yeah, I like what you suggest, Bruce, about thinking of this as kind of different substructures in phase space, let's say. But the problem that in theory, I think that would be a great way of doing it. And in practice, I think one of the problems is that, of course, there's a continuum often between a lot of these different structures. So, for example, maybe from the halo to the inner halo to the bulge, they might not necessarily be very distinct. They might be a continuum. We don't know, as is the case also with the discs, for example. And the other problem I see is that sometimes some of these are the same. So, for example, the thick disc and the bar and the boxy peanut. How do you distinguish these, right? Because the bar is forming out of the disc, so they're one and the same as well. And there's a thin disc, there's a thick disc in there. So at least in the Milky Way, where we have detailed chemistry, that seems as a kind of cleaner way of defining things, because then you can talk very specifically about a specific, population that can have certain kinematic properties. So maybe that becomes a bit cleaner to talk about these different structures. But yeah, I'm not sure I have very clear ideas on this, but
no, yeah, you say a cleaner division if we look at the abundances rather than the kinematics.
Yeah, which is not possible maybe in of course in external galaxies,
Yeah.
but at least in the Milky Way.
Yeah, good point. Christina, thanks.
Oh, sorry, I had just a comment for something that Mike said, but I now forgot.
Oh no.
Sorry.
We'll come
But
back to
I
you.
think it was about the bar that he said there is a segregation of populations. I mean, the segregation of populations is, I wouldn't call like this. I mean, there you see that the stars that are right now in bar orbits, they have everybody there. They have metal poor component, they have metal rich component, and they have high alpha and they have low alpha. So this is a structure. It's not a population. That's why I was not surprised to find everybody on the bar. They're just surfing around, but who was already there before and who came later, I don't know. I just see that there is a component in the bar, let's say with bar-shaped orbits, taking all the caveats of how is to get those orbits, which is also a big problem. But I just can see that some metallists go even higher for the stars that are in the bar. So you have a metallist distribution function that shifts from 0.2 dex to 0.25 dex. So that may be saying something about this bar formation mechanism and the gas that was put there. So I think this is a great constraint for some modeling, probably.
So maybe I just heard Christina say the structure, the kinematic structures are a little more distinct in some cases than the chemical structures. So there's a different way of looking at it. Victor?
Yeah, I just wanted to get back again to something else that Mike said. He said multiple times now that he is surprised by the clumps because he expects to see a distinct chemical signature in the bulge from the clumps. And I'm just puzzled by what it is that you're expecting to see, Mike. We've studied a little bit clumps in my group, and one of the things the clumps do is they have high star formation rates, so they self-enrich and they evolve in the chemistry. So, and they produce lots of alpha elements, and there is an alpha-rich population in the bulge, as we've seen many times. What is it different that you're expecting to see or thinking that you should see?
Yeah, Mike, go ahead. Can you unmute it, Mike?
Yeah, okay.
Quick answer.
So quick answer is that some clumps are bigger than others, are more massive than others. Therefore, they might have extreme alpha abundances in the stars. There might be a range in alpha abundances, perhaps even a range in heavy element abundances if the R process origin, is merging neutron stars that are rare. Short answer.
Okay, but why is that a problem? I mean, there is a range of elemental abundances across the bulge. Why does having a range of elemental abundances in the clumps present a problem for the bulge if you're creating a whole bunch of them?
It depends how many clumps. If it's a handful, maybe you would expect to just see, as in Emily's early model, peaks in alpha to Fe, peaks in magnesium, unusually high. I'm just throwing this out as something that will be interesting to keep an eye out for. It might also be that our bulge didn't form from a galaxy that was dominated by big clumps. We have a bar, maybe it formed from a disk, and the clump era vastly predated the disk, and most of the stars that we have today dated from the time the bar was formed. And by the way, to mention the bar, that everybody agrees that the metal rich stars are more concentrated toward the plane. So within the bar, there is some substructure. I'm just throwing this out as a challenge. Maybe in M31's bulge, we'll see the signature of ancient clumps because it's not a bulge that formed from a bar.
Okay, good point. Madeline, you're next. And Peter, your hand is still up. If you want to have a question, I'll call on you next. Madeline?
Yeah, I was wondering, we're talking about seeing different chemical signatures. I was wondering what people think we would expect for a classical bulge be chemically different than a boxy peanut bulge or the inner halo, for example. How would we chemically, without dynamics, decompose those populations?
Good question. Who would answer that? Christina, do you want to take a crack at that? How would a classical bulge?
that's something I have been looking at. So first of all, I don't expect that because you have a clump with a high star formation, you're going to have a different alpha over iron level. The alpha over iron, unless there is a first star that did some weird stellar yields, but assuming that we haven't seen this in other very old populations in the thick disk, I don't know. But I wouldn't expect a different alpha over iron level. That I would expect if it turns out that these clumps were forming stars with a more top heavy IMF. Then I would expect a different level in alpha over iron. What I would expect is that a population that's forming something very efficiently, which seems to be the case of the clumps, then I would enrich very fast. So I would achieve a larger metallicity value in a shorter time scale. That's why I said that if these clumps end up in the bulge, and if I start seeing that the plateau in alpha over iron extends to larger metallicity than the thick disk, alpha over iron versus metallicity, then this will be an important signature. But that's why I'm also making the effort to move in then to the end capture elements. When you come to the end capture elements, you know that in the galaxy metal pool, you have very large scatter, and you have to model that. And that's related to the sources of these elements. And what we were trying to do and are trying to do in this paper that we never finished is exactly to check if we have a signature of different scatter in the bulge and in the halo, for example. In a situation where you have less stochasticity because it's more concentrated, it's more star formation efficiency, so you could change the stochasticity of how you produce those elements. But a different alpha over iron, I don't expect.
Thanks. Peter? Okay, so well, I'll just take another minute.
Oh.
Go ahead, Peter.
Sorry, I was going to say I had accidentally left my hand up, but then I actually did have a very brief comment,
Yeah, go
which is about M31, which turns out to have about, its bulge seems to be about 1/3, something like a kinematically hot spheroid, and 2/3 a boxy peanut bulge of a bar. So M31 may not be as nice and simple as maybe some people are hoping.
Mm-hmm. Okay. We've hardly gotten to these other two questions, but the answer, I'm guessing, is going to be that it'll take a long time to answer them well. Can we simulate this wide dynamical range anytime soon? You know, if it's a factor of 1,000, considering softening lengths and so on, to give you even the bulge region, let alone without the nuclear region. You've got 1 billion elements in there, and is that something we can expect or even done already? And similarly for the observations, how we can observe them locally, but that means we can't see how they form at high redshift. And in both cases, if we can't really simulate these nor see how they form at high redshift, where are we? How are we going to figure out theoretically the simultaneous formation of all of these structures and how they may interact? And if there's a quick comment on that, we could take it, but I do want to go to Livia, who has another set of questions for you. Does anyone have a quick comment on how we're going to figure out the simultaneous evolution of these, either from direct observations or simulations? Seems quite a challenge because of the large dynamic range. Okay, something to think about. That's, oh, Francesca.
Yeah, maybe just a quick comment is it depends what kind of context we want to do that in. So from cosmological simulations, that will be quite challenging, of course, because of the very different scales that you need. But I think in isolated simulations of kind of isolated galaxies, we are seeing, we are seeing results coming out for these nuclear regions myself, but also there's been previous results published also from Victor's group as well. So I do think that we can get answers about these nuclear structures, but from a cosmological context, for the nuclear, really small structures, that is quite challenging still.
The softening length for those calculations, is it in the parse?
So yeah, softening lengths, and then also the mass of the particles themselves, and trying to get to higher resolutions.
I just lost connection quickly. Anyway,
there was
thanks,
one more
Francesca.
question by
let's
your
move on.
Laura. Yeah, there is one more question
Livia.
by Laura Origlia. No.
I just want to add to what Francesca said. That
Can you?
Becoming,
go ahead, Livia.
Sorry, can you hear me?
Yeah.
So I just wanted to add to what Francesca said. It's actually possible also in a cosmological context to go to such high resolution, and are the simulations, the zooming simulation by the FIRE group that start to reach those scales. Maybe, I mean, it's not yet really comparable with isolated runs, but they're getting there. So that was all.
Okay. So in the next 15 minutes or so of this discussion session, I would like to focus on some challenges and future perspective on tools, and in particular, I would say on three aspects, somewhat related one to each other, that could be especially relevant for the science that has been discussed in this conference. So it's a matter of fact that we have to face complexity, and we have to deal with the multi-parameter space that includes information on kinematics, chemistry, but also age, mass, star formation, and many other parameters probably. So this is definitely a challenge for observations, data analysis, and comprehensive model. So your opinion on that is very valuable. Also, both observation and simulations have the problem, I would say, of trading off resolution and coverage in many respects, thus requiring wise but not necessarily trivial decisions and synergic multi-off efforts. So I think it's an important topic to discuss. And finally, since we are approaching a new era of super performing telescopes and computers, we certainly want to get ready and exploiting their power at maximum. So we may want to design optimum experiments where possibly observation and modeling are comprehensively accounted for. Indeed, often we can only match model predictions and observations that have been obtained from independent science projects, hence not necessarily optimally linked one to each other. So I think this is also an important point for our community to discuss in view of the future capability. So discussion is now open on these three aspects, and if there are other that you want to bring to the attention of this community are also welcome.
So let me first emphasize that first point, that we've seen in this conference several really interesting and novel talks about the use of machine learning techniques to segment out the different components in this highly complex intermixture. And it seems that's a clear direction for the future. And yet, of course, there's the older way of just concentrating on single components, isolating them in one way or the other, on distance kinematics or whatever. So I think we'd be interested in discussing, hearing more from you, what you think is the future of this, and how much should we try to shift the community with training and examples in this new direction for something as complex as the inner region of a galaxy.
Christina?
Yeah, this is something that is worrying me a lot. We have been trying several things with machine learning and chemistry, for example, to look at a large dimension space with several elements. And sometimes it's very promising, but it really requires very good balances. And when they are not there, when they are problems, which are normal problems, calibrations, differences that happen in different parameter space of log G, metallicity, then you start getting weird answers. I mean, not weird answers, you start getting things that are not really real, that are just artifacts. And you have to be able to figure them out. So for that, I think there is no machine learning without the standard also in parallel. That's how I see it.
Mm-hmm. I was quite impressed by the 2 or so talks we heard. One with cross-training a couple of days ago, and another with more of the neural network approach. And of course, we see other applications which are very powerful. But you're right, there has to be some expert in the loop, so to speak, to know when there are pitfalls or problems, because it could come up with something spurious.
Madeline?
Yeah, I was just gonna say that other thing with machine learning is you get what's ever in your training sample. If there's something that's not in your training sample, then you're not going to find that. You're going to lose the space for discovery in that way. So you really, you're really confined by the parameters of your training sample as well. So it's can almost be hurtful in some ways if you're looking for anomalous things a lot of the time.
Yeah, so if we put in 1 million Gaia orbits, would we get the distinct features that we see in the nuclear region, in the bulge region? Curious, could it segment those out and tell us what we see morphologically? And if they're too few of a particular type, you're saying, Madeline, quite right, we wouldn't see it. So somehow, maybe we're not ready yet for some aspects.
So any question on trading off resolution and coverage? Any comment?
Yeah, I mean, the problem both for simulations and observations, and it's related to the points I made before, the large dynamic range. Is it just a matter of time before everything is observed, all the high resolution patches are finally covered? Or is there some quitting point where we have enough, we've learned enough with a few very high resolution patches, and in which case we move on to other galaxies? If we cover everything, we're more likely to solve the problem Madeline just introduced, that we're not going to miss anything.
Dimitri?
Yeah, I'm on the point of resolution, but maybe I am a bit changing gears to extragalactic, but this is something that Oscar also mentioned in his talk. And I think spatial resolution is crucial for the central region. We've seen this with Muse, not only with Timer, but a number of other studies looking at nearby galaxies with Muse, where with good spatial sampling, all these structures are becoming a lot more evident in not only kinematical maps, but even metallicity maps, age maps. And you see a lot of different structures. And also something that there was some discussion on Slack, and Eric Kempson was also joking that apparently what we call classical bulges are becoming smaller and smaller and less important the better we look at the central regions of galaxies. That maybe this is the last bulges conference. I don't know about that. It's a joke, right? But I think, yeah, the point is that spatial sampling is crucial, I think.
Christina?
Very quickly, I think spatial sampling is important outside the galaxy and in the galaxy, but another high resolution information we need is age. And when I see the extragalactic age, I'm not sure this age has the resolution I need to see what I want to see. And in the Milky Way, we see things different if something is 10, 11 gigayears and something is 8 gigayears. So many of the data seems to be still at redshift 1, while we want to be in redshift 2. So I don't know, Kundar is at redshift 2, Anke is already at redshift 2, but a lot of others are still in redshift 1 inside the Milky Way. So I think, resolution in age is necessary.
Okay, thank you. Federico?
I have a comment and a question to follow up what Dimitri just said about classical bulges becoming smaller and smaller. So, I mean, in the classical picture, the classical bulges were built by major merger or some other types of violent processes that we think are, an essential ingredient in the lambda CDM cosmology of hierarchical merging. So I'm now starting to think whether, these observations that came to light, that the classical spheroids are becoming rarer and rarer is actually, maybe a bigger problem that we have to consider.
Yeah, I mean, if I can comment, I
Yeah,
guess
sure.
the others also can comment. Yeah, I think this has been noted, right? There is even a paper by Jim Peebles last year where he comments on this, that if you look at nearby galaxies, you don't see a lot of dynamically hot spheroids in the center. There are papers also from the time of collaboration that we also looked at many galaxies and we don't see classical bulges. Of course, the timer sample is biased towards biased galaxies, so it's not the best sample to do this, but still, the absence of classical bulges was noticeable. And whether this is a problem or not, I don't know, because you in cosmological simulations, you can see hierarchical growth in the cosmological simulations, but still leading to galaxies that don't host a major central spheroid. And what I think is happening is that the importance of mergers is getting towards earlier and earlier time. So like redshift 4 or above, where we actually have a lot of activity and mergers. So I think what you're saying, it's an open question. I think it can be a challenge, and we still have to see, but both from the theory and from the observations, because we don't have really a good census of the amount of classical bulges in the local universe. There are studies like what Simon was mentioning the first day, but there are lots of caveats to those studies as well. So I would argue that we need a lot of kinematical measurements for a complete sample of nearby galaxies.
Okay, thank you. So, any comment on the possibility of designing optimum experiments, fine-tuning observations and simulations in order to get maximum of scientific answer?
Yeah, and can we use machine learning techniques, optimization techniques to design experiments? If we postulate an experiment to get a certain result, we'll see how close that is to mapping out what we think is there. In the way we could fine tune that, and it wouldn't just be one; it would be a suite of observations. It would be, AMA, ELT, Rubin. What do we need to optimize to get the most amount of information that we're interested in the least amount of cost, for example, right? It's an optimization, and it implies, I think, a community approach, which is something Livia and I were discussing also. What is the future of our study? And with this complexity, are we driven to more and more of these amalgamating workshops where we get to talk about everything as a community? And are we forced to observe with a coherent strategy as a community? Mike.
Yes, I think that we really would benefit not from just having large numbers of rapidly derived compositions and abundances. I think that we need to try to get the quality of abundances from these large surveys to be as high as if, to reach the level of quality that individual analysis of the stars would attain. we need a new generation of machine-derived abundances that will, because otherwise I worry we're just not going to get, we're going to be deluged with millions of stars, but perhaps very not well-determined abundances and compositions, and that may not help us.
Can we use small samples at high quality to do cross-training for large samples at lower quality? I mean, we heard something about mixing samples, and this is really Livia's questions. We have this choice of wide samples that are shallow in some sense, or narrow samples that are deep. And what can we gain by mixing, or is it just confusing? Will we get the wrong answer if we mix?
I worry that, I think this is a question for the people, that I think that that the machine learning can be improved. Certainly, I think that all I'm saying is that I worry about, the million, for example, what are we really going to get a lot from Sloan 5 if the spectra are lower signal to noise ratio and abundances of lower quality? We can already get 0.2 dex abundances from BVBS for 3 million red clump stars for FE/H. But if we're going to, on the sunniest day, trends of composition are not as constraining as we once thought. Back in the day, I thought that, McWilliam and Rich showed the bulge was enhanced in alpha elements, and now it's like, if anything, barely enhanced relative to the thick disk. So, if we're going to be deriving all of these compositions, publishing them and using them, we need to kind of have a breakthrough in terms of the quality of measurements that come out of these different surveys. For example, one survey in Apogee has a flat alpha to FE versus FE/H, but another has a big break between high and low alpha, and yet others show steep declines in alpha. These are things we're going to have to resolve and all agree on from the highest quality analyses if we're going to employ the chemistry to get us insight into how the bulge formed. Similarly, we'll have to model those abundance distributions that we now have. Perhaps outflows were very important. I think outflows may have been important, particularly in the outer bulge. I'm talking too long.
Yeah, thanks, Mike. I guess, Livia, with your permission, we might wrap up. We want to save
sure,
some time
because it's time to leave
Elena,
the floor.
Dimitri. Just on behalf of Livia, myself, and many of you, I do want to thank you for organizing this. I have learned how we can have a remote meeting and still be highly effective and highly personal. We can communicate. This has just been an eye-opener for me. And of course, I would much rather be with you in person. I get up at 2:30 in the morning here to be with you virtually, but it's just been fabulous. So thank you, and I'll turn it back to the SOC and LOC.
Thank you, Bruce.
I will also thanks a lot to the LOC for all the work they did, not only this week, but also the previous week in preparation of this meeting. And also, I would like to emphasize one more the importance of acting as a community. And we discussed that with Bruce. Bruce already mentioned that, but we have to act as a community to really face all the challenges we have in front of us. And we are fortunate to have challenges and to have a future, but we have to get organized to take the best of this opportunity. So thanks a lot, and room for the LOC for the final discussion. Thanks.
Thanks. Francesca, do you want to?
Yes. Okay. So thanks, everyone. And we had just we made a quick, we gathered our thoughts together with the rest of the LOC. So we thought we'd share with you kind of some closing remarks, which is really just a scattered compilation of the LOC's takeaways from all these great talks and all of the great discussions that have happened this week. So first to say that we've learned a lot. I mean, I've definitely learned a lot from all of the discussions and all of the talks. And something that I think came out of all the discussions is that there's a growing consensus in the community that the central regions of galaxies are occupied, I'll be careful with what I say here, not bulges, but the central regions are occupied by a number of different structures. These have come up various times during the week. We've also just brought these up, like nuclear disks, boxy peanut bulges, spheroids or dispersion dominated structures, etc., even though we don't always agree on the names. I think something that's come up that I find quite interesting that Eric also brought up in the discussion is, where are all the classical bulges, in the sense that in the local universe, in the Milky Way, and for detailed local universe studies that we see, with high resolution IFU data, we're finding fewer and fewer of these very hot spheroids, it seems, although there's still, of course, room for debate, but it's definitely not as much as we thought before. So is there a growing tension between what we're seeing in the local universe and what we're seeing with, large statistical studies at kind of intermediate redshifts? And I have, no answer for that. And I think there's many different ways of, maybe there isn't a tension, maybe it's just different ways of looking at things. But these are some of the questions that came to our mind when we were, discussing what we take away from the conference. One, theme that's reigned supreme throughout the conference is that terminology and nomenclature matter. So it seems that it's quite difficult to come up with a consensus on naming, but there is a growing awareness by the community that there's some issues with some of the terms like pseudobulges, and that these might, incorporate many different structures. And we need to be really clear and define clearly what we mean when we discuss all of these different structures. And yeah, there seems to be some progress from simulations, especially from the cosmological simulations, in producing kind of more realistic disk-dominated systems. But are they really reproducing, faithfully enough what we're seeing in observations? And there was a great talk by Mark about this, and how do you go about comparing more accurately what we're seeing in the simulations and what we're seeing in the observations, also in a very kind of large, statistically accurate way. On the topic of clumps, there's been a lot of, I've definitely learned a lot about the clumps, and there's been a lot of, I think, takeaways from there. I think one of the main things is that it's unclear still how much clumps at high redshift contribute to the bulge buildup. And this depends really sensitively on how long lived and how massive they are. And this in turn, depends really sensitively on the strength of stellar feedback. So this is still a really big open question. And there was a lot of great talks touching upon different aspects of this. So, for example, that it seems that their stellar mass content is small, that they appear to be long-lived, and there's a lot of great steps forward also in terms of the CO detections of clumps. And I think there's no strong consensus yet on actually what kind of bulges these clumps form. So I think there's maybe more work to be done there also from the modeling side, even though there's a lot of great simulations already there. And when we look really at the higher redshift universe, dynamical studies are seeming to find that bulges, or protobulges, are already in place at very, very high redshifts, and they're hosted by dynamically cooled disks. So I think it's very interesting to see that these structures are forming really, really early on, and they in some ways look similar to what we see in the local universe. And I'll hand over now to Elena, who will say a bit about Milky Way.
Just a few words on what we think are the takeaway message regarding the Milky Way. We have seen really a consensus on the fact that the Milky Way hosts primarily a boxy peanut structure formed out of bark instability and in situ population. And what it was nice to see is that there is an agreement between models, but also a fairly good agreement across a very different spectroscopic survey. What I think still one of the hottest topic in the formation of the Milky Way in the region. It's really the age. I think is still not completely sorted out. And so that we should question ourselves how we can solve this, how we can get more accurate ages. And then another point that I think it came out from the talks, a very nice talk and discussion, is the characterization of the most metal poor population. We have seen, we've started seeing a more study on that, and here we just list a few talks. But I think well, we'll see in the next in the next year, in the near future. But I think it's the metal poor population. So with metal poor, I mean more metal poor than -1 dex, will deserve more observation, but also attention from simulation and modeling. And I think this would also it will also be greatly facilitated by the next an imminent survey, thanks to the new facility. And then I really want to finish and this short wrap up with a warm thanks to Stella Maria, who you haven't seen because she was in Nilma. They were extremely helpful. They've been working a lot on the background, as well as a huge thanks to Camila, Tucto, and Alonso. They have been, I don't know, I should say more than great, because really they help us, they facilitate, they help us to facilitate the discussion. And if we had a very smooth workshop with not a lot of tech problem, it's really thanks to them. A big thanks to the SOC for helping us in shaping this very nice conference, and with the great contribution. And of course, to all the speakers and all the participants. We might not have a final answer how to call bulges or how they are formed, but I think that we, at least we have done a good job in settling a little bit the stage and try to connect more the people from different community. And finally, I really want to thank my colleagues Francesca, Dimitri, and Lodo and Anita, because they've been very great and helpful. It wasn't easy to organize this conference, because at the beginning we started and we were all in Munich, and then with the pandemic, the year passed, and Francesca and Dimitri just left, and they actually moved from Munich to UK basically a few days before the start of the conference. So you can imagine it must be very stressful for them. So thanks a lot. And I hope to, and for the youngest people, we hope that with this workshop, we helped in setting connection and network. Now you see, you know people from different community, and the Slack channel will be on so for longer, so you can keep interacting. The video will be available for much longer. So just enjoy watching the talk and interact with each other. Thanks a lot to everyone. It was really, really great.
Thanks, Elena, also for your efforts. Thank you, everyone.
Pleasure.
Thank you.
Thank you.
Take care and see you.
Thank you, everyone. Goodbye.
Ciao, ciao.
Ciao.
Bye-bye.